Okay, so we are going to, I'm not going to prove this theorem, but this is a converse of the theorem we proved in the beginning. It says that provided the real and imaginary parts have continuous first order partial derivatives in a domain, this is sometimes called being C1. There's C1. Uh, if in addition to that, they satisfy the Cauchy-Riemann equations, then the corresponding function of a complex variable is analytic on the domain, or analytic in D. So this is a converse to the theorem we proved in the beginning, and there's this additional C1 condition. And this C1 condition shows up over and over and over in analysis. It's normally what you need to suppose in order to get a nice result like this. And this is a great theorem. So it says roughly that the theorem earlier is an if and only if. So let's use this as an example real quick, in an example. So we're going to look at the function, which has real part x over x squared plus y squared, and then imaginary part y over x squared plus y squared. You might notice, if you remember doing real and imaginary parts, that this is the function 1 over z, or equivalently, it's z bar over modulus z squared. So here, u of xy is that guy, and v of xy is this guy, but you have to include that negative sign. Okay, so let's write them out. U of xy, just to be clear, is x over x squared plus y squared, and maybe we'll put v of xy over here. V of xy is, make sure to include the negative y over x squared plus y squared. Now this is the function, again, 1 over z, which is z to the negative 1, which should, by the power rule, be differentiable everywhere except for 0. And we're going to recover that. Okay, so here, our domain, what's the color for a domain? Maybe over here in orange, so it pops out. Our domain is C minus 0. Okay, so the non-zero complex numbers. That's an open connected subset of C. And U and V are certainly continuous on D. Let's compute the partial derivatives. So we have to apply the quotient rule, right? So we take the derivative of the numerator, which is 1, times the denominator minus the numerator times the derivative of the denominator with respect to x, which is a 2x, over x squared plus y squared. We're going to need to use this, so let's simplify a little bit. We have an x squared plus y squared and then a minus 2x squared. So I think that gives us minus x squared plus y squared over x squared plus y squared. And then similarly, let's do v. Then I'll scroll down and do the partial derivative with respect to y's. So we're going to do vx. So the numerator has no x's in it. So we're just going to, so there's no, if we take the partial derivative, we get 0. So we're just going to subtract off the numerator times the partial derivative of the denominator with respect to x, which is 2x. Oops, I'm missing a squared here. And then x squared plus y squared squared. And that's just the quotient rule, of course. So take a moment and do that if you need to. Now, uy is again just the quotient rule, and now the roles are kind of reversed. So our uy here, the first term is 0, and then we're going to get minus x times the partial derivative of the denominator with respect to y, all over the denominator squared. And then, let's see, oh shoot, I didn't simplify. Let's see, negative, so that's going to be a 2xy over x squared plus y squared squared. All right, and then vy is going to be, okay, so now the numerator contributes. So we're going to get negative 1 times x squared plus y squared, and then minus y times the derivative of the denominator with respect to y, which is 2y over x squared. Keep missing my squareds in the denominator. I think I got them all now. All right, let's do some simplifying for these guys that we just computed. So let's see, we get negative 2xy over x squared plus y squared squared. And now let's be careful with our negatives. So we're going to get a negative x squared, and then we're going to get a negative 1 y squared, but there's going to be a plus 2y squared. So negative 1 plus 2 is 1. Okay, now let's compare. Ux is supposed to be equal to Vy, and in fact, they are. They're just equal on, dang, I keep missing my squares. Sorry, y'all. They're equal on the nose. And then uy and vx are supposed to be equal up to a negative, well, with a negative sign. So this expression is supposed to be negative of vx. And surely it is. It's negative 1 times that. And so the Cauchy-Riemann equations are satisfied. And since the Cauchy-Riemann equations are satisfied, we can deduce that our function, this 1 over z function, is of course analytic, which is something we already knew. So thus ux is vy and uy is negative vx. So f is analytic on c less 0 by the theorem. Great.